We have seen how to set up a vector diagram when a boat travels in a river that has a current. In this case, we have a plane that flies from city A to city B. So we can treat the plane like a boat, and we can treat the wind like the current in a river. We start off by considering that there is no wind effect. So the pilot heads out from A to B and reaches B in the same path that he headed out in. Let's draw the vector diagram for this case. Since the pilot heads out in a direction from A to B, the vector Vp with respect to W is horizontal. This is a case of no wind, so the vector Vw will be absent. Therefore, the plane will follow the direction that it set out in. So vector Vp, the velocity of the plane with respect to the ground, will be identical to the velocity of the plane with respect to the wind. This is the simplest case with no wind. Now let's bring the wind factor into the equation. Let's say there is a wind blowing towards the southeast direction. The pilot heads out along a line joining A and B, so that is the vector Vp with respect to W. And the orientation of the plane is parallel to the line AB. The wind is blowing in the southeast direction, so that is represented by the blue vector Vw. In this scenario, the plane will drift away from its destination, which was point B, and the plane which heads out from A to B ends up traveling along the vector Vp, and this is the direction as seen by a stationary person. Now let's look at this mathematically. The vector Vp with respect to W is Vp minus Vw by definition. We rearrange this so as not to have a negative sign in the equation. So we get Vp equals Vp with respect to W plus Vw. Vp with respect to W is the direction that the pilot sets out in, and therefore is also the orientation of the plane. Vp is the actual direction the plane ends up traveling in. So you have to remember that the resultant vector is Vp, much like in the riverboat problems where the resultant vector was Vb. Vp is the velocity of the plane with respect to the ground. So this is as observed by a stationary observer. But unlike in a riverboat problem, where you can end up anywhere along the shore, a plane has to necessarily land at an airport, and that airport is B. So there is a constraint here. We cannot afford to have a drift if we are to land at B. So the pilot must head out as shown along vector Vp with respect to W, also seen in the orientation of the plane, parallel to the vector Vp with respect to W, so that when the wind velocity vector Vw is added to it, the resultant vector Vp is horizontal, or is aligned with the line joining the cities A and B. So this is the principle that we have to use when solving plane wind problems. And just like the riverboat problems, it is important to get the velocity diagram right. Once you have that, then the rest is purely mathematics. Plane wind problems follow the same basic principles as the riverboat problems. The plane can be thought of as a boat, and the wind can be thought of as the river current. In the vector diagram, the velocity of the plane with respect to the ground must be aligned to the path connecting the two cities.